Thank you.
You're welcome. Hey, good morning, everyone. Uh, this morning I looked at all your homework. First, I was surprised that almost everybody except two people submitted a homework. That was the first time. All the other two homeworks, we had like 7, 8 people missing each time. But this time, only two people decided it's below them to submit homeworks, but they're the one that's going to lose points. In any event, I want to solve homework number 3 on the board. And if you do have some time, we go back to chapter 14 and continue talking about it and practicing it. I hope you guys have your textbook with you. And if you don't get a chance today, hopefully next time, next Monday, please make sure you bring your textbook with you so you can follow and do this exercise. Again, I'm trying to do this for you guys to boost your grade up. So help yourself. You're not helping me, just help yourself. Okay, let's see how many people we're missing. Now, about 9 people. All right. The first problem was pretty straightforward, very easy. We have a temperature of 10 degrees at 0.1, minus 10 degrees, I'm sorry, at 0.1. And then we have a pressure at 600 kilopascal. So we organize ourselves. First thing we do the TS diagram, we put all the information. And they said, from the COP, however, if the mass of refrigerant is 7 kilograms per second, find the total loading, cooling load. So to start with, again, as always, we start with state one. We have T1 equal to minus 10 degrees Celsius, and obviously X1 is equal to 1. That means the saturated vapor. So we go to the table, regular saturated liquid table. This time we look for H1, which is in this case is H of G, and S1, which is S of G. So these two values are 244.55 kilojoule per kilogram, and S of G is 0.93782 kilojoule per kilogram degree Kelvin. So that's the first H value. At state two, we have P2 equal to 600 kilopascal and S2 being equal to S1. Now we go to superheated table because the point is located at superheated region. And this time we find the value of H2, which is 267.19 kilojoule per kilogram. At state three, P3, which is equal to P2, is equal to 600 kilopascal. This time, X3 is on the saturated liquid line, which is X3 is equal to 0. Now we can find H3, which is in this case is H of F. And that value is 81.50 kilojoule per kilogram. Finally, at the state 4, we have expansion valve. Therefore, delta H is equal to 0. Now we write H4 is equal to H3 is equal to 81.50 kilojoule per kilogram. Please remember in your final exam, if you don't do this fourth step, and right here just H3 is equal to H4, you're going to lose, 3-4 points. So don't do that. Don't forget that. You need to be clear in your communication. You have to show your work. You have to tell the readers, where did you get that idea that H4 and H3 are equal? Why? And this is the explanation, because of expansion valve, and that's why delta H cross the expansion valve is 0, therefore H4 is equal to H3. Don't forget to make sure you have it. Now that we have all the H values, so the COP is equal to QL divided by work in. Now the QL is H1 minus H4, and the work in is H2 minus H1. That's our work.
Fantastic email is that's a screenshot of what the makeup quiz 3 for Blakey gives me.
Hello?
Gives me.
Are you asking a question or are you talking to somebody?
I apologize. I didn't know I was unmuted. I was sending an email. I was reading out loud. Sorry.
I still don't get it. Okay. So we have H value, H4, H2, and H1. So once you plug the number in, you will find the value of COP. to be 7.20. That's the first part of the problem. Then we say if the mass is 7 kilogram per second, what would be the QL? Well, the QL is equal to the mass times a small QL. That would be the mass of refrigerant times H1 minus H4. Now, if we do that, plug the number in, you find the value of QL to be 1,141 kilowatt. Very simple, straightforward. And again, if you organize yourself, there is no way that you can make any mistakes. Any questions? Okay. Now the next question, there are efficiencies involved. So this becomes 2S and this is 2A. Now, point 1 is located in the superheated region. So is point 3 located at compressed liquid. So now that's the TS diagram. Now, one thing that you need to pay attention, the problem said that we remove the heat. Keep in mind, this is the QL, and this is the QH. We remove the heat with water. That means you have the water enter at 18 degrees Celsius, leave at 26 degrees Celsius at the condenser. That's how we remove the heat from the cycle. And the mass of water is given, let's see, to be 0.25 kilogram per second. Now, write it on with this part so I can erase it.
Yes.
Is it okay if I erase this part of the first problem?
Yes.
All right. Now, one thing you need to understand when you have a situation like this, that means the QH of a refrigeration cycle has to be equal to the Q of the water, because this QH is removed by the Q that's going to be added to this water. So in one side, we have the mass of refrigerant times H2A minus H3. On the other side, we have mass of water times H2 of water minus H1 of water. Of course, there is another way of doing this, and that is mass of water times Cp of water times delta T. Either way is correct. So by having the mass of the water in one side, we can easily find the mass of refrigerant from the other side. So this becomes very important for us to determine the mass of refrigerant so we can solve the problem. Now, the temperature at point 1 is given, temperature at point 3 is given. The temperature at point 2 is given, that's point 2A, not 2S. Every time you have a temperature given, that is the temperature of the actual value, not isentropic value. So in that case, we start at state 1. We have P1 equal to 60 kilopascal. Let's write this. And we have a temperature at point 1, which is minus 34 degrees Celsius. Now, point 1 is in a superheated region, so we go to superheated table, and we find the value of H1. In that case, H1 becomes 230.04 kilojoule per kilogram. Since the problem didn't tell us what is the efficiency, we don't have to find the 2S value. And the problem didn't ask us to find the efficiency of that, cycle. They just give us the temperature and pressure for that point 2A. So I don't need to find the S1 value. And at state 2, I have P2 equal to 1200 kilopascal. And I have a temperature at point 2 that is given to us to be 65 degrees Celsius. Once again, in superheated table, I find the value of H2 to be 295.18 kilojoule per kilogram. At state 3, we have P3 equal to 1200 kilopascal, and also we have a temperature at point 3 to be 42 degrees Celsius. From saturated liquid table, we find H3, which is H of F in that table, and that will give us 111.25 kilojoule per kilogram. Once again, at stage 4, we have expansion valve. So that gives us delta H is 0. Therefore, H4 is equal to H3, which is equal to 111.25 kilojoule per kilogram. So we run out of cycle and we find all the H values. Now we come back to this relationship in order to find the mass of refrigerant. Now, mass of refrigerant times H2A minus H3 has to be equal to the mass of water times H2O. Hello, please turn off your microphone. We don't want to hear the background noise.
Sorry.
H2 of water minus H1 of water. Now, if we go this route, we can easily go to the water table and based on the temperature that is given to us, find the H value. This is the hardest way. The easiest way is we have the mass of water, CPR water, for your information, we can get it from the table, is 4.18 kilojoule per kilogram degree Kelvin. And delta T, what is delta T? 26 minus 18 is 8. So you have 8, 4.18, this is 0.25. You can solve it much faster. I decided to just do it the hard way so you guys can get the hang of it, but you have always two choices. Now, to find these values, they're at 26, no, first one is 18. At 18 degrees Celsius, you go to saturated liquid table and find the value of H1 on water to be 75.47 kilojoule per kilogram. At 26 degrees Celsius, same table, you find H12 water to be 108.94 kilojoule per kilogram. So now I have all the information here except mass of refrigerant. So if I plug these two numbers here, 0.25 kilogram per second that is given to me by mass of water, I have H2A, I have H3, so I can easily find the mass of refrigerant to be equal to there's one thing I missed. 0.459. Or 9 kilogram per second. Now, one thing I missed, they asked us to find the quality at 0.4. So one of the thing was finding the quality at 0.4. Now, how are we going to do that? If you look at that, at state 4 right here, we have H4 being equal to 111.25 kilojoule per kilogram. The second information that we have, that P4 is equal to 60 kilopascal. These are the 2 points of reference. If I go to the table, I can very quickly find the value of the quality at 0.4 to be 0.4796. And this one doesn't have any unit. You don't have to worry about the unit. That is part A of the problem that I forgot to do. Again, once you get to 0.4 and you find a value, state 4, and you find a value of H4, the next thing you do, based on that H4 value and based on the pressure at 0.4, which is same as 0.1, you go to the table and you find the quality, and that is the quality at 0.4. Now that we have this, they ask us to find the QH, QL, WN, and so on and so forth. So the QH is mass of refrigerant times H2A minus H3. You plug the number in, you find that to be 8367 kilojoule, kilowatts. Also ask us to find the work in, which is work of a compressor, and that's mass of refrigerant times H2A minus H1. And this will give us 2.513 kilowatt. Now they're asking us to find the QL. Well, there are two ways you can find the QL. The difference between these two will give you QL. That's a much easier, faster. Why? Energy balance equation. We have only three energy components in this cycle. The work that we put in, the QH that we're removing, and the QL that we're producing. Summation of all energy has to be equal to 0, or what comes in has to be equal to what goes out. So if I take the difference between these two, it will give me the QL. That's one way. The other way is just saying the mass of refrigerant times H1 minus H4. Or I can say QH minus W in will also give me the QL. I will always do that because it's quicker and faster to go through this one. Either way, you get the exact same answer. If you do that, your value of QL becomes 5.404 kilowatt. So that's your QL. That's the QH that they ask for, and this is the Q, the work in that they ask for, and that's the quality. So the last part is finding the COP. So the COP is equal to QL divided by work in, and in this case, we have the COP of 2.15. Now, the reason this number is a little bit lower because we have efficiency of the compressor. We don't know how efficient it is, but that will have a major effect in our COP. Now, the last part of this problem, I wanted you guys to solve that problem up to this point, but I couldn't tell you that. The last part is total nonsense because it's just one of those crazy ideas whoever wrote this book tried to get across that make absolutely no sense. They're asking you what would happen if we have a perfect cycle. A perfect cycle is a Carnot cycle. And a COP of a Carnot cycle is totally different. The COP for Carnot cycle is equal to 1 over TH over TL minus 1. This is the COP of a Carnot cycle. Now I'm saying if we consider the same condition, however, it happens to be a Carnot cycle, which is not, what would be the COP of that? Okay? The highest temperature we have is at 0.2A, which is 65 degrees. The lowest temperature we have is minus 34, which is at 0.1. If you apply that in, then you end up with a COP value of 5.063, pretty close to 2.5 times of the COP that we found for this cycle. Now I say if that is the COP and we keep the work in the same amount, what would be the new QL? So new QL would be the COP times work in. If you do that, that becomes 1272 kilowatt. Again, 2.5 times of what we found originally. Now, this part, you will never get it in your test, and you never find it anywhere, and that's totally nonsense. But because it was there, I just wanted to show you how it's done. So just don't worry about it, because it just doesn't make any sense. You're taking this cycle and assuming this is Carnot cycle with the same condition. That's just, total nonsense. Any questions?
I had a question.
Sure.
How did you know state one was in the superheated region and not on the line?
Where is it? Look at the TS diagram.
Yeah, that's what I mean. How did you know to put it there instead of on the line like some of the other problems?
If you just go back to your notes, when we started, we said the actual cycle, if the 0.1 is here, it's just a saturated, vapor. However, if you are given pressure and temperature, 0.1 is automatically in superheated. What do you have on 0.1? You have pressure and temperature.
Okay, gotcha. Yeah.
At 0.3, you have pressure and temperature. That's why 0.3 is also outside of this quote unquote dome. It's in a compressed liquid area rather than being in a saturated liquid.
That makes sense. Thank you. Yeah.
Not a problem. Not a problem. That's what I'm here for. Any other questions? I'm glad you guys asking this question, because if you don't, that stick with you, and later on you have no idea what happens, and then you make mistakes. So no question is a stupid question. Just feel free to ask any question you want. Any other questions? So please don't forget that water, as I mentioned before, we always use external resources to remove the heat, or when we create a cooling, it has to go somewhere. We either make ice with it, or air conditioning, or refrigeration. So always something connected to this, and always something connected to that. Could be air, could be water. So don't forget that. Now, I'm not going to do the 56. I want to do the 59, problem 59. Now, let me know if you're done with this part so I can erase this. I'm sure.
Actually, Professor, I had a quick question. Can you kind of walk through the state 3, like how you can get the HF of state 3? Because like at 1200 kPa, the T sat is 46 something. So I was wondering, like, it's not like, it didn't seem as easy to.
Well, you have to interpolate, my friend.
Mm-hmm.
At this pressure, and this is the temperature that is given to you. So you might, definitely you're not going to find HTD just by looking at these two numbers. So obviously, you need to find out if you have there for 46, look at the 41 or whatever, and then interpolate, then you find out.
Okay. Okay. Got it. Thank you.
Not a problem. This is, unfortunately, there are a lot of interpolation in what we do in this course. But that's what you do when you're at home doing the homework, because you have time. But again, don't forget, if you have a test, something like that, I'm sorry, you just make an assumption based on the numbers you see. You find numbers somewhere in between that you feel is realistic, just put it down and just move on. Because nobody cares about how correct your answer is. as long as your approach is correct. All right. Now, problem number 59, I'm sorry, is the cascade refrigeration cycle. We're going to do that. And let me just do the diagram first. This is basically the diagram. This is our cycle A, this is our cycle B. And the main focus on this one is making sure what is happening here in the heat exchanger. We know that net heat exchange in a heat exchanger is zero, meaning the QL of this cycle. If we color this part, what do you see? You see the QL of that cycle. That QL of cycle A has to be equal to the QH of this cycle. So this QL will remove the heat from this cycle. At the end, we will have only one QL and one QH and two workable compressors. Now, this particular problem what we need to write here is the mass of refrigerant A, which is at the top, times H5 minus H8. H5 minus H8 has to be equal to the mass of refrigerant B, H2 minus H3. That is the relationship that we, having one mass flow, we can find the other one in order to solve the problem. Now, the TS diagram our point 1 is unsaturated vapor going up to point 2, point 3, coming back to 4, and connected to 1. However, they told us that the efficiency of a compressor is 80%. So this is basically 2S, and this is our 2A. That's 0.1. Here, we have 0.5 going to 6S. This is 6A. That's 7, 8, and going back to 5. So this is the TS diagram. Now, as you notice, I left the space here because I want to write that correctly. 2A, that's a H2A minus 3, H3, not 2S. You always use the actual value. So that's a relationship that we need to think about. I guess the mass of one of the refrigerant is given. I don't know which one. Okay. The mass of refrigerant B is 0.25 kilogram per second. That means I have to find the mass of refrigerant A through that relationship. Now this is very simple and a straightforward problem. When we start at the state 1, we have P1 out. That's another thing. The pressure at 0.1 is given to 160 kilopascal. 0.2 is 500 kilopascal. Now, if you recall, I mentioned that there is no pressure drop on the heat exchanger. The pressure remains the same, but the heat will change. However, in a real life, there are some pressure drops that we cannot ignore. So this example is a real, actual example. Now, the pressure between 5 and 8 are given to be 400 kilopascal. So I noticed that few people make that error on their homework. They consider this one is 500. Do not make any assumptions. Because of the routine, we keep the pressure the same, but you need to read the problem carefully. And if you read it carefully, you realize these two pressures are different. So don't just rush through it. Read it very carefully. And of course, at the top, we have 1400 kilopascal. So I have all my information that I need on my TS diagram. I know the relationship that I need to take care of. I have the efficiency. I have one of the mass flow rate. So all I need to do, find H1 to H8, then I'll be home free. So at state 1, I have P1 equal to 160 kilopascal and X1 being equal to 1. That means it's a saturated vapor. So I find H1 and S1. Again, this is SOG, and this one is HOG on that table. The value of H1 is 241.14 kilojoule per kilogram. That's 1 out of 8. And this one is 0.9420 kilojoule divided per kilogram degree Kelvin. At state 2, I have P2 equal to 500 kilopascal, and I have S2 is equal to S1. So now, a superheated region, I find the value of H2S. because we cannot find the actual value from the table based on S1, S1 being equal to S2, I can only find the H2S value. Once I find out, I take the next step to find H2A. So the value of H2S is 646, 264.25 kilojoule per kilogram. But this is not what I want. I want the actual value. The efficiency of a compressor is a work of a compressor isentropically divided by work of a compressor actual. That means H2S minus H1 divided by H2A minus H1. I have H1, I have H2S, and this side is 0.80. The only unknown would be H2A. From there, I can find the value of H2A to be 270.41 kilojoule per kilogram. That's what I wanted. Now, again, everything has to make common sense. At any given point, you can check your answer, see if you're in the right track. Look at this. H2A is 270. H2S is 264. Look at your TS diagram. I'm sorry, 2S has a lower temperature than 2A. Obviously, 2A, because of the higher temperature, has to have basically higher H value. And that shows, so I'm in the right track. If this number was less than that, I've done something wrong in my calculation. Either that, or I didn't write the equation correctly. So be very careful on that. Always check your answer, see if it makes sense. 241, going up to 64. This is 241, this is 264, this is 270. All makes sense. That's what we have here. Now we go to state 3. At state 3, I have P3 equal to 500 kilopascal, and X3 being on the saturated liquid line is equal to 0. So this time I find the value of H3 to be 73.32 kilojoule per kilogram. At state 4, I have expansion valve, therefore delta H is 0, so H4 is equal to H3 and is equal to 73.32 kilojoule per kilogram. That's my lower cycle B. I'm done with it. Now I go to state 5. At state 5, I have P5 equal to 400 kilopascal, and I have X5 being equal to 1. Once again, I'm repeating exactly what I did at the state 1 and 2 and 3 and 4 to repeat myself basically. Everything that I've done here, do it here as well. So this will give me H5 value and S5 value. The value of H5 is 255.61 kilojoule per kilogram. And the value of S5 is 0.9271 kilojoule per kilogram degree Kelvin. Now, since I'm done with the diagram, I don't need it anymore because I transfer everything into my TS diagram. And also I need the space. So now, at the state 6, I have P6 equal to 1400 kilopascal, and S6 being equal to S5. So I will find the value of H2S, I'm sorry, H6S. That value becomes 281.56 kilojoule per kilogram. Using the same concept here, efficiency of a compressor, which is equal to 0.80, is equal to H6S minus H5 divided by H6A minus H5. From there, I can find the value of H6A to 288.04 kilojoule per kilogram. Now, in state 7, I have P7 equal to 1400 kilopascal and X7 being equal to 0. So I can find H7 value to be 127.25 kilojoule per kilogram. Now, I need to write the same statement that I did for state 4, for state 8, but because of I don't have enough room to solve the problem, I just simply do this equal to H8, but you don't do that. We need to be very clear and just write it, the statement. So now I have all H values, so I go back to my original equation in order to find the mass of refrigerant A. So now, mass of refrigerant A times H5 minus H8 is equal to mass of refrigerant B times H2A minus H3. Now, the mass of refrigerant B is 0.25 kilogram per second. I have H2A, I have H3, I have H8, I have H5. The mass of refrigerant A would be the only unknown. So if I plug everything in, I will find the mass of refrigerant A is 0.3839 kilogram per second. Now I have the masses, so very simply I can find QL and the work in. Now QL, I have only one down here. QL is equal to mass of refrigerant, so I call it B, times H1 minus H4. This is 0.25, H1 and H4 are calculated. This, if I do it correctly, should be 41.96 kilowatt. Now the work in total, because I have two of them, is equal to the first one, which is mass of refrigerant B times H2 minus H1 plus mass of refrigerant A times H6A minus, oops, I forgot this. H2A minus H1. This would be H6A minus H5. Now looking at this, I have both masses. I have H2A and H6A, and I have H1 and H5. Once I plug it in, my total work in becomes 19.77 kilowatt. That's my QL, and that's my work in. Therefore, the COP is a QL divided by work in. This will give me 2.12 COP. Once again, the reason this number is very low because our compressor are not 100% efficient. It's only 80% efficient. If we didn't have that 80% efficiency, this number would have been pretty close to 3 rather than being 2.12. But this is basically a real project. It's pretty close to the real. Any questions? No question? Okay. Now, going back to problem 56, first of all, this is not going to be on your test, on your final exam. By the way, your next week exam is chapter 10 only. Don't waste your time looking for anything else, just chapter 10. Don't forget to have all the tables ready, both, steam tables. There are 4 tables you have to have: saturated liquid and superheated. In SI unit, and saturated table and superheated for English unit. Don't forget to have those 2 handy in front of you. Now the next problem is the one that we told you is pretty expensive to begin with, very expensive to operate, and at the end of the day is not going to make any sense, to go through that headache to do it, because it's not going to give us the efficiency that we are looking for. So, and that's where most of you have problems finding the quality at 0.6 and how to manage it and how to do it. I solved exact identical problem like this. The only difference between this one and the one I did on the board is just the numbers were different. But the process, procedure, everything is exactly the same. Now, do you want me to go through that and solve that problem for you, or go back to chapter 14 and practice that one?
I just had a question of at the very end of the way you solved it in class, calculating the work in. So in what I did, what happened in the notes, basically, it seemed like I don't know how to describe this like easily, but I wasn't sure if you needed to, like in your notes, it didn't seem like you used the quality, or I guess the X6 in calculating the work in of the 2 compressors. And I was wondering why that was the case.
I still don't get your question.
Yeah, it's kind of hard to describe because it's the very end of the problem.
Okay, what do you mean?
But it's okay. I can ask you after class.
Okay, all right. Any other question? But I still need an answer. Do you want me to solve that problem here, or you want me to move forward and go back to chapter 14? What's your preference?
Could you solve the problem, please?
Okay.
Thank you.
All right, the TSI now for that problem. Oops. This is a TS diagram for that problem. Again, if you consider this is A and this is B, this is where you are mixing the refrigerant at 2 points. One is here, point 2 comes to point 9, point 3 goes to point 9, and then it goes up. That's where you mix those together. Here, you're splitting at point 7, portion of it goes to point 6, the other portion comes out to point 8. So the direction is basically going that way, here, here, coming back. That would be the direction of that. At the end, we will have 1 QH, 1 QL, and work on one compressor, let's say compressor 1, work over compressor 2, or compressor A, compressor B, however you wanna do it. Now, what you need to find out that what is that quality, how much of this become a vapor and goes this direction, and how much of that is the liquid coming this direction to go to evaporator. That's the crucial part that we need to find. Now, based on the information that is given, I'm gonna do it the short way because we don't have that much time. So I have the value of H1 becomes 234.46 kilojoule per kilogram. The value of H2, of course, we have to find S1, then go to the pressure at H2. Keep in mind, pressure of H2, 9, 3, 6, 7, they're all in the same pressure line. 1 and 8 are the same, 4 and 5 are the same. Don't forget that. So the value of H2 becomes 262.70 kilojoule per kilogram. Now, H3 has the same pressure at H2, but X3 is equal to 1, the same way that at 0.1. So we can find the H3 value to be 255.61 kilojoule per kilogram. Now, since we don't have any information here for now, we leave it alone. We go to state 5. So state 5 has pressure of 4 and 5, and X5 being equal to 0. The value of H5 would be 127 0.25 kilojoule per kilogram. And the value of this, because of expansion valve, this is also equal to H6. And H7 has an H70 with this pressure. So you will find the H7 value to be 63.92 kilojoule per kilogram, which is also equal to H8. Now, to find the quality X6 is equal to H6 minus H of F divided by H of F of G. So based on this pressure, we go to the table, find H of F, find H of F of G. I already have the value of H6. I can easily find the quality at 0.6. And that quality becomes 0.3304. That is the quality. That means 33% going that direction and the balance of it comes this way. So now, in order to find 9 and 4, I need to do an energy balance equation between 0.2, 9, and 3. Again, summation of all energy going in has to be equal to summation of all energy going out. Now, what goes into 0.9? I have M2, H2 going to 0.9 plus M3, H3 going to 0.9. And at 0.9, I have M9, H9 going on. Now, at 0.2, if this is going to be X, and this is going to be 1 minus X, so that would be 1 minus X6 times H2 plus 0.3 is the X that's going that direction. So X6 times H3 is equal to 1 unit times H9, because all here is all 1 unit. And if you do that, you will find the value of H9 to be 260.35 kilojoule per kilogram. Now that is this, I have that. I go to the table to find the value of S9 based on this H9 value and P9, which is the same as 2 and 3 and 6 and 7. I find the value of S9 from the table, and that would give me 0.9438 kilojoule per kilogram degree Kelvin. So that would be S9. Again, this P9 is 400 kilopascal. And H9 value, we can find S9. Now that I have S9 is the base of the second compressor. So I can say at P4 and S4 being equal to S9. Of course, P4 is 1.4 megapascal. Based on these two, from superheated table, I can find the value of H4 to be 287.10 kilojoule per kilogram. So now I have all 9 H values. Now, if I consider that the mass of the cycle A would be 1 unit, be 1 unit, this is 1 unit, or the top one, 1 unit. You can find basically the other mass by saying 1 minus x6. So the QL, well, I want to find the QL. The mass flow rate here is 1 x minus x6 times h1 minus h8. I have the value of x6, which is 0.339, and I have h1, I have h8. If I plug it in, I will find the QL value to be 28.55. 28.55 kilowatt. Finally, find the work in. Now, the first compressor has 1 minus x6 times h2 minus h1 plus, this has 1 unit only, that would be h4 minus h9, and you add those two, they have the Qing value of 11.41 kilowatt. Finally, finding the COP, that's the QL divided by work in, and that gives us 2.50 coefficient of performance. Any questions? Again, there's nothing that you need to worry about, but in general for you, if you want to understand what's happening, again, we have 2 cycles, the masses of the refrigerant, although it's the same, but they mix at 2 areas, at 0.9 and here at 0.6. Because 5 comes to 6, then 6 is split to 7 and 10. And 3. Portion of it goes this direction, the balance of it goes the other direction, coming down here. So if this is 1 unit, come down to here, x6 going that direction, 1 minus x6 coming all the way down until to 0.2, then x6 will add 2.9, make it 1 unit, and from there it goes 1 unit, 1 unit, 1 unit. So if you understand that part of it, and you understand once you find all the H values, utilizing an H6 and the pressure at 0.6, which is a 400 kilopascal, going to the table, finding H of F and H of F of G, plugging it here, you find the quality. Once you find the quality, you go back and take care of it, this relationship. 0.2 comes to 0.9, 0.3 comes to 0.9, and 0.9 goes up. So based on that, 1 minus x6 is times h2 plus x6 times h3 has to be equal to 1 unit times h9. Now that we found the value of x6, we can easily find the value of h9. Once we find it, we go to the table. Based on that and based on the pressure, we can find S9. Now, finding H4, of course, we have a pressure. We have S4 is equal to S9, so we can find H4. Now I have all my H values. My QL very simply would be H1 minus H8, but there is a fraction in front of it. I work in one compressor has a fraction, the other compressor has 1 unit, and that's exactly what we did. And then dividing QL by work in, you get your coefficient of performance. Now, when we get together Monday, I expect you to bring your textbook. And again, if you have ebook, please print those two psychometric charts, because you're gonna need that for the final exam anyway. But it would be great that we can do some practices together. Just get comfortable with it, so you can spend only 1 or 2 minutes on your final exam and get a 15 points. So if you guys want to still talk to me and stick around, if not, have a good one, and I'll see you guys Monday.
Excuse me, Professor, I have a question.
Sure.
So this goes back to chapter 10 for the I think it was the open water feeder system. So I understand in that one that when we're looking for one of the points, it depends on the pressure of the water feeder, whether like it'll be treated as superheated or a mixture based on whether it's greater than or less than 600 kilopascal.
Right.
Does that also apply to the reheat and the cogeneration cycles or not?
That applies for reheat, that applies for feed water, that applies for cogeneration. Yes, any pressure above 600, that point is going to be on a superheated region.
Okay, thank you. Because I was like, I was trying to study the cycles a couple of days ago for the exam, and I was just trying to make sure that I was understanding the cycles and the points right for the TS diagrams.
Yeah, the TS diagram, again, if you have anything above 100, that goes to basically the superheated region. That point is going to be outside. If it's less than that, then it's a mixture. Then you have to worry about solving 2 mixture points.
Okay, thank you so much, Professor.
No problem.
Have a good weekend.
You too. Thank you.
Thank you, Professor.
Well, my pleasure. No problem.
Professor, I'd like to go back to that problem where I was asking about state 3, and you said you said I needed to interpolate to find the right H value for state 3 on sorry, let me go back to that problem on problem 1122.
Okay.
So I'm a little, I guess, yeah, there's something I'm misunderstanding because I don't know which values to interpolate between for that state.
You need to look at that pressure. Let me go back because I don't memorize these things. Okay, at the state 3, you have the pressure and you have the temperature.
Yep.
Pressure is
1200 kPa.
kilopascal, and the temperature
It's 42 C.
42 degrees Celsius. So when you go to 1200 kilopascal, what do you see as far as the value of H?
At 1200, the value of H is 117.79 for HF.
Okay, very, very good. You said 117 what?
0.79.
Okay. This is what you find at that pressure.
Yes.
Now, what's really getting the temperature, forget about the pressure, look at the temperature. What do you see on that temperature?
For that temperature, 2, H of F is 111.28.
Okay. 111.28. Okay. Now, what did we say that H value was? 111.25.
Yeah, that's what you wrote down.
Okay. Now, if you look at these two, as you can see, if you go with the pressure, that's 117. If you ignore the pressure, go with the temperature, it's 111.28. Now, I picked this number, of course, is very accurate because I do it with the computer. It will take care of all of those things. However, from your point of view, any number that you pick between these two, that's good enough.
Oh, okay.
Because
Got
Arthur,
it.
you need to understand, don't get stuck on the answers. Get stuck on a process and a procedure.
Yeah, for this, I just didn't know if we
No,
chose the
you-
lower one, there was like
you
energy
have-
loss, so I didn't know.
No, you have spent a lot of your time, your valuable time, focusing and thinking where that numbers come from. Why is that? Don't worry about it, my friend. I said it over and over and over. This is not important. What is important right in this process that because of that, I get this number. Who cares about this is accurate or not?
Okay. Okay.
Numbers are not important. Please do not focus on a number.
Okay.
Focus on the number and answers, the more valuable time you lose to actually think about the right way of solving a problem, and then you end up with nothing. Don't do that to yourself.
Okay. Got it. Thank you.
Not a problem. Anyone else?